Hello and welcome to the Daily Space. I am your host, Dr. Pamela Gay,
And I am your host, Beth Johnson.
and we are here to put science in your brain. Now, we know that all of you have JWST on your mind, and we promise we're going to talk about it. But today's episode still has news to get to and a guest to talk to.
Joining us later on in the show is Hamed Valizadegan, the project lead for ExoMiner and machine learning manager with the university's Space Research Association at NASA Research Center. He'll be here to talk with us about the ExoMiner project and what it is doing for the search for exoplanets.
As a science communicator, there are certain emails I have come to expect. By and large, the most common of these emails are the, "Hi, I need your help with my math, but I have a solid explanation for why relativity is wrong and I just need you to do the math for me." First of all, I have no idea what I have done that would ever make someone think I'm willing to do theoretical physics as a favor for them. Second, relativity is true. And while it has some not well-defined corners, the parts of it that we have worked out have been proven over and over and over through myriad experiments. One of the best laboratories is naturally occurring. 16 years ago, astronomers discovered a pair of pulsars in a binary system. These fast-rotating stars are like cosmic metronomes, with one flashing the beat every 44 seconds, while the other does so every 2.8 seconds. While the stars themselves, in their pockets of time and space, are the most perfect metronomes in the universe, what we see is affected by the distortions of relativity. A quick glance may not reveal these effects, but over the past 16 years, those distortions have added up to yet more definitive proof that Einstein was right. Over the years, researchers have been able to watch the elliptical orbits rotate so that the long axis of the orbit changes its alignment. What they see matches relativity perfectly in all its finest details. They can also see the orbits shrinking as they radiate away energy in the form of gravitational waves. And here's the thing. Since energy and mass are the same thing, this lost energy is no different than lost mass. This is the first system that can be measured so precisely that this matters. This system has a lot of firsts. The effects of frame dragging actually make it possible to figure out the radius of the faster of the two pulsars. And that radius is just 22 kilometers or almost 14 miles. One set of maths, general relativity, is able to completely and consistently explain this system. Nothing else can do it. General relativity is true. So please, stop emailing me your alternatives and asking me to do your maths. Einstein was right, and the universe has complex order we need to savor. This work was led by Matt Kramer and appears in a pair of papers in Physical Review 10.
Outer space defies a lot of what seems like common sense based on how we humans experience the universe from the surface of our planet. Things like gas take on an entirely different meaning when their motions are dominated by gravity instead of thermodynamics. Gas can form structures, and according to new research led by Jonas Syed, those structures include a filament that stretches 3,900 light years across the disk of our Milky Way. Made of atomic hydrogen, this material contains clumps, or clouds. Molecular hydrogen can form and collapse into clouds that may one day be able to fragment into stars. This structure was named Maggie by co-author Juan Soler, who named it after the longest river in his home country of Colombia. This case stands out in images of hydrogen gas, and measurements show the velocity of the gas is constant across the strand. This is a reminder that our galaxy is still young and active and has the fuel to continue to evolve new generations of stars and planets. And, well, the rest of that sentence I leave to the science fiction authors to write.
Exactly how the gas of the universe slowly evolves from the clouds we see to worlds like the Earth we live on is not entirely understood. We have big picture ideas, but they're like a mural painted with a giant brush. The ideas are there, but the details are lost. To understand what happened, we need to understand not just how gravity evolved structures, but also how chemistry evolved content. We know the end result. Our world has been magnificently changed by time, geochemistry, and geophysics. And in the end product, and it is the end product of a water cycle, carbon cycle, plate tectonics, and more. Understanding how it started. Well, that requires samples. And lucky for us, the Hayabusa II mission has returned a 5.4 gram sample of material from the asteroid Ryugu. This 900-meter across space rock is too small to have the kinds of processes we have on Earth. And its material is more like the unmixed ingredients of a cake dripped onto the counter than like the mixed and baked result that is our Earth. Early analysis shows this material is visually dark, looking more like grains of pepper than regular sand. The material is also porous, like ground pumice, with a chemistry like the most common meteorites found on Earth, the carbonaceous chondrites. How this asteroid got to be so dark? Well, researchers are still working on that. Who knew the solar system was filled with goth space rocks hiding against the blackness of space? After the break, we're going to be back to talk about an infrared observatory that, if it works, will have the ability to see the warm glow of space rocks in alien star systems, and a whole lot more. Stay tuned. This morning, I saw the most accurate headline of the year. On Slate, editors wrote, "Astronomers are freaking out over the launch of the James Webb Telescope." NASA seems pretty darn certain that the JWST is going up on Christmas Eve at dark 20 for most of us here in the Americas. That's 12:20 UTC, 7:20 a.m. Eastern, and 4:20 a.m. Pacific. Sorry, Beth. This telescope is named after a NASA administrator who is controversial and may have been part of the lavender scare at NASA. For this reason, we will always refer to this scope as JWST. This is a huge telescope. The idea of iterative design was thrown out the window as NASA jumped from telescopes that could launch in their final form to a system that origamis into its rocket fairing. Made of 18 hexagonal mirrors, the infrared telescope has a 6.5 meter diameter and is kept cool with a series of baffles that block sunlight and air gap, or rather vacuum gap, the scope from any heat. It is the hope of the astronomy community that this massive system will be able to collect enough light to reveal the first galaxies and stars forming in the universe and resolve worlds orbiting nearby stars. This is not a replacement for Hubble. JWST is something new, working in wavelengths more like Spitzer or Herschel. This is the single most expensive system for science we have ever attempted to put in orbit. Originally planned to go up in 2007, it is also over budget, over schedule, and is the financial black hole that ate the funding that might have otherwise fueled countless careers and smaller observing systems. The cost for this was paid not just in dollars, but also in how many jobs could exist in our field and how much research could be done. The entire astronomy community is currently holding its breath, waiting to see if what we paid was worth it. If everything works, the answer will be yes. But there is a lot that could go wrong. We will be hosting a launch party on twitch.tv/CosmoQuestX to watch whatever happens Christmas Eve. I will probably not be on stream. I may be in the background, calmly having a panic attack or drinking eggnog, or both. Both is an option. This is your reminder that space is hard. Back in 2014, I was giving a seminar on how to cover live events with social media when Orbital ATK was gearing up to launch an Antares from Wallops. On board was the Arcid 3 satellite from Planetary Resources. This was the perfect teachable moment. There was a crowd-funded satellite going up on a young rocket, and it was all going out on NASA TV. And then the rocket blew up on launch. It was still a teachable moment, but not the kind I was looking for. A few years later, when I was filling out standard forms to hire a new social media person, I checked crisis communications as a needed skill, and as a required example, I put communicate explosion of rocket carrying project-related spacecraft. I was thinking of OSIRIS-REx. HR rejected my form and said this was not a realistic concern, and I wish I shared HR's emotions on this topic. At this point in my career, I've had one telescope I needed fail to function on time. HET, I'm looking at you. One X-ray telescope just plain fail. Hi, Astro E. And despite transforming my career to mostly use archival data, I had a grant put on hold when HST ran into issues and required servicing back in 2009. This is the life of an astronomer. We are at the whims of government funding, the functionality of our equipment, and our lives are punctuated with the explosions of rockets carrying the hopes and dreams of our future research. Right now, the hopes and dreams of 4 generations of astronomers are sitting on top of a rocket in French Guiana. Once the rocket launches, and we aren't that worried about the Ariane 5 misbehaving, we get to hold our breath through the release of the fairings, and then we have to wait and see if this sucker can unfold all its bits and bobs. Unfolding is problematic. From Skylab's solar panels to Galileo's high-gain antenna failure to most recently seeing Lucy's solar array not latching correctly into place. Moving pieces have lots of ways to disappoint, and JWST has a lot of unfolding to do, and this is scary. Oh, and there are over 300 single points of failure. Sometimes it is best to emotionally prepare for the worst. Back in the summer of 1994, comet Shoemaker-Levy 9 plunged into the surface of Jupiter as a string of falling ice chunks. I was at Kitt Peak that summer as a student, and while we were prepping to observe, we were all told to expect nothing. It would be easier if we expected nothing and nothing happened. I now go into every launch expecting the worst, while a tiny voice still somehow screams and cheers while expecting the best. As we go into the launch and deployment of the JWST, remember, space is hard. Everything or anything could go wrong. Failure is always an option. But we must dare mighty things and expect the worst while nurturing that tiny voice that still dares to dream. We will see you Friday morning at Dark 20. Bring eggnog. After the break, we'll be back to talk with our guest about using machine learning to find more exoplanets. Stay tuned.
Welcome back. Last month, we brought you the story of how scientists used a deep neural network called ExoMiner and NASA's supercomputer Pleiades to comb through Kepler and K2 mission data in an attempt to speed up the process of finding and confirming exoplanets. In a release published at the end of November, they had cataloged an astonishing 301 exoplanets. Joining us now, Hamed Valizadegan, the project lead for ExoMiner and a machine learning manager with the university's Space Research Association at NASA Ames Research Center. Thank you, and welcome, Hamed.
Thanks for having me.
Very glad you are here. First off, will you give a really quick explanation of what a deep neural network is?
Sure. Let me start with the artificial neuron. A neuron is a simple processing unit that gets multiple, one or more inputs, process it, and send it out. Now, in a most basic version, a neuron computes the weighted sum of its input, applies a nonlinear function and send it out. A neural network is many such neurons working together to solve a problem. Usually they are organized into layers. And when we say deep neural network, we are referring to a neural network that has so many such layers.
And how did you apply this technique to exoplanets?
Yes, so, depending on the type of neurons and the structure of the neural network, we have different types of neural networks. So there is one special neural network called a convolutional neural network. This is the type of neural network that is useful for images and time series. And we basically use domain knowledge in order to design the high-level architecture of this convolutional neural network. We have different branches specialized to process different diagnostic tests that are designed in order to identify different types of false positive for in this domain. So there are different branches working together, each responsible for a specific type of diagnostic test. And we train the model using Kepler data.
So what can cause a false positive in the transit method that Kepler uses?
Yes, so there are a bunch of different false positives. So in order to explain it, let me explain what transit photometry for planet discovery is. So we take pictures, like Kepler takes pictures every 30 minutes, and we look at the star and see whether there is a dimming or reduction in the brightness of the star. If that happens, and if it is periodic, that means that there is something's orbiting that the star.
Mm-hmm.
But this could be an exoplanet. This could be an eclipsing binary, two stars orbiting each other, depending on their configuration. That could be actually that could show a signature similar to an exoplanet, but it is not. It is an eclipsing binary. It could be systematic noise, meaning that you have, just because the instrument is not producing some noises, but we see some periodic event that is not an exoplanet, but it behaves like an exoplanet. It shows periodic behavior, and it shows the reduction in the brightness, but that is just noise. There is a third one, which is due to background object. When we say background object, we should note that just in the Kepler view is in average 35 pixels. So this is quite amazing that we have only 35 pixels. We have such pictures every 30 minutes. By those videos, we want to know whether something is orbiting or not. But it's easy to get contamination from a nearby star. And if there is a transit signal that is near on that nearby star, we feel that this is on the target star. And this is, again, another type of false positive.
All right, well, I want to talk to you some more about this model. But first, we're going to take a break, and then we'll be back with more from Hamed and the ExoMiner project. So stay tuned. Welcome back. Once again, I am here with Hamed Valizadegan talking about the ExoMiner deep neural network and finding exoplanets. So, Hamed, will you describe how ExoMiner is modular in design and why that makes a difference in validating potential exoplanets?
Yes, so by modular, we mean that, so like I said, there are different types of convolutional neural network. There is a special, different types of neural network. There is a special one called convolutional neural network. We have different convolutional branches that process each one of these diagnostic tests that are developed by domain experts for this problem. So each branch is separately extracting feature and analyzing a separate diagnostic test, and each one is designed specifically for that diagnostic test. That's why we call it modular, and the advantage is that it provides explainability, so we can explore what input, what diagnostic test trigger the false positive or not.
So, what comes next for the project and for you?
For the project, so there are three main directions that I'm very excited to pursue. One is just application of ExoMiner, or well, let me call it ExoMiner version 2, because we have, improved ExoMiner since submitting that paper. So it's a bit better now. We cannot wait to report the result on tests, and I'm hoping that at some point we can validate new exoplanets from the test data. Second is explainability. We reported the explainability in the paper. It is a very basic version of explainability. Since then, we have a much more sophisticated method. This is much more accurate, and we are putting a paper together. The explainability framework that we have developed is not only going to work for this problem, for many problems that have a specific property. So this is a new methodology. And we are going to publish paper for both, machine learning, conferences and astrophysics journals. The third direction, I pointed to it a bit, that there is label noise in the data, and a lot of people are concerned that we want to have more clean, set of exoplanet and false positive. We have started, this last semester, with the help of an intern, we started to investigate what portion of these, label data is noisy. Again, this is going to be a tiny portion, but this is important to know. If we are saying something is exoplanet, they are for sure exoplanet. This is an extremely difficult task, but we are working on it, and I'm hoping that we can, have some result on that. For me, I'm going to continue doing the science. I love applying machine learning to science problems. Every time I enter to a new domain, I learn something new, fascinating, and, it's fun. So I'm going to continue that.
Well, thank you again for joining us today, Hamed. Good luck with the ExoMiner project, and we hope to have you back on soon to discuss on the next set of discoveries. So thank you.
Thanks so much for having me.
This has been The Daily Space.
You can find more information on all our stories, including images, at dailyspace.org. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.